Welcome, technical partners, to this explainer. Today, we're jumping straight into a fast-track exploration of the CSDL version 1.0 engineering blueprint. We're going to objectively outline a framework that perfectly translates mathematical constraints directly into physical dynamics. And hey, we're skipping all those lengthy mathematical derivations today. Instead, we're focusing purely on the core, verified conclusions and the exact engineering specifications. By the end of this explainer, you're going to have a clear, rigorous understanding of how this architecture maps precise logic right onto physical hardware to solve some incredibly complex problems. So think about the traditional computing model we all know and use, right? You have systems executing sequential lines of code, one by one, to generate a result. Well, I want you to contrast that with a completely different paradigm we call configurational computing. This is entirely based on variational principles. Instead of executing step-by-step instructions, it works by constructing an array system that's actually capable of physical relaxation. By relying on fundamental, rock-solid physical rules, things like Kirchhoff's laws, electrical potential differences, or thermodynamic gradients, the system automatically seeks out its lowest energy state. And here is the profound takeaway from all this. That stable, lowest energy configuration that the system naturally settles into, that is your computational result. It's literally physics doing the processing for us. To make this physics-driven processing a reality, CSDL utilizes a strict computation by constraint design, and it's built on 4 abstracted layers. Let's start right at the foundation. Layer 1 is the physical layer. What's absolutely brilliant here is that CSDL is entirely hardware independent. Whether you're working with CMOS circuits, photonic arrays, piezoelectric actuators, or even high-fidelity Python digital twins, it just works. We simply map a state vector to a physical node's analog voltage, pressure, or temperature, and a control vector to the tuning voltage applied via a digital-to-analog converter. Moving right up to layer 2, we have the constraint layer. This establishes the absolute physical rules the array must follow, and it does it without needing complex mathematical proofs to enforce them. A really prime example of this is the magic hypercube constraint. This dictates that the sum of state variables along specific lines, like your rows, columns, or diagonals, must always equal a constant value, which we call m. Layer 2 also enforces strict physical boundaries, like maximum voltage or current clamping limits, keeping the hardware safely and securely within its operating window. Now, you might be wondering, how does the system maintain absolute stability in the unpredictable, messy, real world? Well, that brings us to layer 3, observation and control. This layer utilizes an adaptive feedback loop that combines gradient descent, which quickly pulls the physical states toward the target, with a symmetry restoration mechanism. So if external interference pushes the system out of alignment, this feedback actively pulls it right back. It gives the physical hardware these incredible anti-noise and self-healing properties. Finally, we reach layer 4, the verification layer. This gives us the objective, strictly verified conclusion of system convergence using Lyapunov stability proofs. We literally don't need to guess if the system will settle. It's objectively proven to do so. Plus, rigorous Monte Carlo testing under random initial conditions guarantees a convergence success rate of 90% or higher. So how does this whole overarching architecture translate into a practical, hands-on application? When you interact with CSDL, you'll actually use JSON formatting. But we need to completely redefine what JSON means in this specific context. In traditional software, JSON might just hold data for an executable script. But here, it's not executable code at all. Instead, I want you to think of it as a standardized engineering blueprint, or really a physical genome. This file explicitly defines the topological structure and the control parameters of the physical array. When you load this JSON, you are directly instructing the hardware on exactly how to configure its physical relaxation process. It acts as a direct, one-to-one bridge between digital configuration and physical action. Let's look at exactly how that mapping works in a highly complex, life-critical engineering scenario, a non-rotating pulsatile artificial heart that's powered by a piezoelectric actuator array. It's fascinating how specific lines of this JSON map directly to physical reality. First up, we set our magic constraint M to 12.0. Up in layer 2, this ensures that across all 16 actuator nodes, the pressure and flow totals are always perfectly conserved to exactly 12. Physically, this guarantees absolute consistency in the volume of liquid being pumped. Next, we have the alpha stiffness piezo parameter, and this talks directly to layer 1. It dictates exactly how much voltage thrust the piezoelectric stacks must apply during the systole and diastole phases, basically the contraction and relaxation of the heart. Finally, the epsilon strain wall feedback maps to our layer 3 feedback control. By setting a specific threshold, say -0.025, the system constantly monitors the dynamic strain on the two walls. If blood flow gets too fast, which risks high shear stress and cellular damage like hemolysis, this parameter triggers an immediate dynamic adjustment of the actuator force to protect the biological cells. The code is literally protecting life through immediate physical feedback. Of course, for a system like an artificial heart, we absolutely must be certain of its engineering limits. There's no room for guessing here. The CSDL version 1.4 technical report has rigorously calibrated these exact boundaries. Through extensive Monte Carlo methods, the crucial engineering limit you need to remember is 0.03. As long as background noise or physical interference remains at or below this strict threshold, the array's global synchronization rate securely reaches over 99%. It's incredibly stable. However, this system's physical death boundary, which is the point where interference causes a total loss of consistent relaxation, is explicitly marked and verified at 0.04. What this means is that any physical system applying CSDL possesses a highly specific, objectively verified, and incredibly robust safety window, even when operating in extreme environments. So we've seen how the CSDL framework uses a very strict 4-layer architecture to map mathematical constraints directly onto physical reality. It turns energy gradient descent into a remarkably powerful computing engine. The robustness is objectively verified and the physical link is crystal clear. So, my final question to you as engineering partners is this. By harnessing fundamental principles like energy relaxation, how will you configure your next hardware array to let physics itself solve your most complex computational constraints? Thank you so much for joining me for this explainer.